Hi, so this week we're going to look at the Stevens and Bates formula for working out optimum reverb times for different spaces. Okay, I want to bring your attention to a book before I do that. If you're particularly interested in this subject, it's not a thing that you would have to buy normally, but if you're thinking about going into acoustics, it's certainly a good one to have on your bookshelf, which is Architectural Acoustics by Anna M. Jaramillo and Chris Steele. So picked out a couple of highlights and things that we've talked about before, just so we can look at. So there's things like Clarity C50, Definition D50 as well, which are quite good. There's a nice little section over here which talks about optimum volumes for good acoustics by room type. So for instance, for meters cubed, in a lecture room, the kinds of meters cubed that you're looking at per seat, 4 to 6, 4 to 7 in the theatre, multi-purpose speech music is 6 to 9, and more than 10 meters cubed per seat in a church. So they're pretty good figures to keep you going. At the back, you won't find the Stevens and Bates formula in many places actually. Okay, so it's quoted here on page 222, but it's something that the Institute of Acoustics really like you to use. So I'm going to talk about it in a little bit of detail, and we'll do a worked example. Okay, so the first thing I'm going to do is just write it out so we can have a think about how it works. So T equals R 0.0118 multiplied by V raised to the power of a third plus 0.1070. Okay, so what does it all mean then? So T is our reverb time. So that's going to be our optimum reverb time really, so that will be in seconds. We've got R, which is a rim factor. So R basically just applies for this equation, and what we need then is to know what sort of sound that we want to let out into this room. So R can be one of three numbers. It can be 4 for speech. It can be 5 for orchestral music, and it can be 6 for choral or organ music. Okay, so you can see here that we would obviously in each of these need a shorter reverb for speech, a sort of medium reverb for orchestral music, and a longer reverb for choral and organ music. So that's fine. Then the other thing that we need in here, which is this V, is our volume. So that's just our room volume. And what this will give us is the optimum reverb at 500 Hertz. So it will only work out what our optimum reverb should be at the 500 Hertz band. If we want an optimum reverb for 125, we should add 30%. And if we want an optimum reverb for 4 kilohertz, reduce 20%. Okay, so this follows a rule that we should have slightly more low frequency than we should have high frequency. So with this we can work out 3 very key bands in what we're doing. Right, so I'm going to do a worked example based on the Boston Symphony Hall. So again, let's do a sketch. It's a shoebox design, and it is 39 meters by 22.9 by 18.6. Okay, so the first thing I'm going to do is work out the volume of that. Okay, so it is 16611.66 and it's cubic meters. Okay, so based on that, let's work out for speech what would be an optimum reverb time. So in order to do that, we can then go our T is equal to, our R in this case for speech will be 4. 0.18 times volume 16611.66 to a third plus 0.1070. Okay, so let's work that out. We should be able to do this in one go. Okay, so let's go 4 multiplied by 0.0118 multiplied by 16611.66 to the, let's use a fraction up here, 1/3. Bring that down and add 0.1070 to that, and that gives us 1.63 seconds. So that'd be optimum for speech. Okay, so if you want to know what the difference would be for organ, then what we need to do is change that 4 out for a 6. Okay, so I can run back through this equation. It's going to take me a little while to get back through it, just to here. I can get rid of that 4, stick a 6 in there to look at the difference. So it'd be 2.45 seconds. Okay, so what I'm then going to do is let's take this 1.63, which is our optimum for speech, and let's look at what the other frequency bands should be. So what we're saying is for speech, let's go 500 hertz. Okay, so for 125, we're going to go 1.63 times 1.3, so we'll get 2.12. And for 4 kilohertz, we'll go 1.63 times 0.8. Okay, just realised that that was below where the camera angle is. So that basically gives us 3 key reverb times for this room, which are based on speech. So we've got at 125 hertz, we've got 2.12 seconds. It's a little bit longer. At 500 hertz, we've got 1.63, and at 4 kilohertz, we've got 1.304. So that is what's known as the Stevens and Bates equation.